Hi, I'm Calvin Leung. I'm a retired mathematics and science teacher and elementary principal. Over more than 40 years in education, I've been thinking and wondering about something. For many people, the mathematical algorithms we teach today seem so familiar that they almost take them for granted. For others who say, "I'm not a math person," they don't understand the algorithms and can't remember them. But have you ever stopped to wonder where the algorithms actually came from, or just how old they really are? That simple question set me down an interesting path of research, and it led me to some surprising discoveries. I'd like to share that journey with you. Let's begin with a simple question. How old do you think many of the algorithms and procedures we teach in mathematics actually are? If someone had asked me that question a year ago, I probably would have guessed maybe 80 or so years. The real answer surprised me. I began looking through mathematics textbooks from the 19th century. One of the first was Ray's Practical Arithmetic, published in 1877. Another was Ray's Algebra, Part First, first published in 1848. These weren't rare research books, they were ordinary classroom textbooks used by students of the day. As I turned the pages, I started recognizing them. Long division, fraction procedures, algebraic manipulations, methods for solving equations. Not exactly the same as today, but certainly recognizable versions of many of the algorithms and procedures we still teach in our classrooms. That really caught my attention. It also led to another question. If many of these procedures have survived for well over a century, should we be trying to replace them? Should we invent completely new algorithms or get rid of some of them? At first glance, those might seem like reasonable questions or responses. However, my answer is no. Here's why. Algorithms weren't invented overnight. They evolved over many generations. The methods that survived did so because they worked. Over time, they were refined to become accurate, efficient, and repeatable. Those are still qualities we value today, so I don't believe the algorithms themselves are the problem. But if the algorithms themselves aren't really the issue, something else must be going on when so many students struggle with them. Perhaps we've been asking the wrong question. Instead of asking, should we replace the algorithms? Perhaps we should be asking, what has changed since they were first developed? Because one thing is certain, the world has changed. So let's compare two different worlds. The world of the mid-1800s and the world we live in today. What's changed? Because I think the answer to that question may have important implications for mathematics education. To begin with, there were no calculators, no electronic adding machines, and mechanical adding machines weren't widespread. No computers. If you needed an answer, you calculated it yourself. That meant accurate, efficient, and reliable computation methods were essential. But something else was happening as well. There was a period of rapid industrialization. Public education was expanding. More children were beginning to attend school. As classrooms grew, there was an increasing need for textbooks and for mathematical procedures that teachers could use consistently from one classroom to another. And just as today, many occupations depended on mathematics. Merchants, bankers, surveyors, engineers, scientists, doctors, accountants, bookkeepers. Society needed people who could calculate accurately, so mathematics mattered then just as it matters now. But then another question occurred to me. If mathematics was important, who was actually learning it? Who attended school? And perhaps even more importantly, how many students stayed long enough to complete their education? Because I had a feeling that answer might change the way we think about mathematics instruction today. So I started looking for the answer. How many students actually attended school before 1900? The numbers were quite different from what most of us would set as targets today. Depending on which decade you look at, roughly half growing over time to 2/3 of children attended elementary school. Only a small percentage continued on to high school, less than 3% early on. By 1900, fewer than 7% actually graduated. Take a moment to let that sink in. More than 90% of young people never completed high school. That represents a very different educational world from the one we know today. And that led me to another question. Why does that matter? What difference does it make when we're talking about mathematics? I think quite a lot. So I began wondering, back then, what happened if a student simply didn't get mathematics? What opportunities were available to them? For many people, there were still plenty of productive occupations available, even if they had little formal schooling or never studied advanced mathematics. Agriculture was enormous. Resource industries employed thousands of people. Factories needed workers. Transportation depended on large labor forces. Many trades were learned through apprenticeship and experience. People certainly use practical arithmetic every day, but large portions of the workforce didn't require the level of formal mathematics that many careers expect today. That doesn't make those jobs less valuable. It simply reminds us that society and technologies were very different compared to today. So now let's compare that world with ours, because I think this is where the story becomes especially interesting. Today's economy is almost the opposite. In the late 19th century, more than half of the workforce was employed in agriculture. Today, it's less than 2%. Many routine manufacturing jobs have disappeared through automation and globalization, and today's trades requires considerably more technical knowledge, mathematics, and formal training than they once did. The workplace has changed dramatically. And there's one more important observation. Nearly every career today asks people to reason mathematically in some way, whether it's using technology, interpreting data, working with measurements, or solving unfamiliar problems. Mathematical thinking has become far more important for the average worker than it was a century and a half ago. So that brings me to what I think is the key idea. Are our math needs different? Back then, mathematics acted as a filter for many careers. Today, it's becoming a necessity for almost everyone. We're teaching essentially the same mathematics to a vastly different population for the needs of a vastly different world. I think that's worth thinking about. So if society has changed and the demands on students have changed, should that influence the way we teach mathematics? Notice what I'm not asking. I'm not asking, what's wrong with the algorithms? I'm asking different questions. How can we help more students understand them? How can we help more students become successful? And that's when some other thoughts came to mind. Not mathematics research, but research into human memory. Because if students are expected to understand and remember more mathematics than ever before, perhaps we should ask, what do we actually know about remembering? So what do we actually know about people's ability to remember large amounts of information? Interestingly, one of the most influential studies didn't come from mathematics at all. It came from the world of chess. Researchers compared expert chess players with beginners. At first glance, the experts appeared to have remarkable memories. They could look at a chessboard for only a few seconds and then recreate the positions of nearly every piece. But the researchers wanted to know why, so they designed a simple experiment. In one case, the chess pieces were arranged randomly. In the other, the pieces came from actual games played by skilled players. The question was simple. Would the experts remember both boards equally well? The answer was telling. When the pieces were arranged randomly, the chess masters weren't much better than the beginners. Their remarkable memory almost disappeared. That tells us something important. But when the pieces came from real games, everything changed. The chess masters dramatically outperformed the beginners. They could remember far more of the board, and they could do it much more accurately. So what made the difference? It wasn't that chess masters simply had better memories. It was that the positions meant something to them. They recognized familiar relationships, patterns, structures, ideas that fit together. In other words, they weren't remembering individual chess pieces. They were remembering meaningful patterns. Their knowledge was organized, and that organization made the remembering much easier. That really made me stop and think, because mathematics is also full of patterns, relationships, connections, ideas that build on one another. So I began asking myself a simple question. If meaningful patterns help people remember chess, could meaningful mathematical structures help students remember mathematics? I don't believe students struggle simply because there's too much mathematics. I think many students struggle because they experience mathematics as hundreds of separate procedures. What if those procedures could be organized into a framework that made sense and connected the algorithms thematically? That's the thinking behind Let's Count on Math. I'm not proposing that we replace the algorithms. The algorithms have proven themselves over generations. I'm proposing that we help students understand why those algorithms work by giving them a coherent framework to organize them. If students can recognize the underlying structures, they don't have to memorize every new topic as something completely different. Instead, each new idea becomes another example of something they already understand. That's how meaningful learning grows. So let me leave you with some final thoughts. For nearly 2 centuries, we've continued to teach many of the same mathematical algorithms because they're accurate, efficient, and reliable. But the world our students are preparing for is very different from the ones those algorithms first served. Perhaps the next significant improvement in mathematics education won't come from inventing new algorithms or getting rid of archaic ones. Perhaps it will come from helping students better understand the ones we already have and seeing how they are interrelated. That's the goal of Let's Count on Math, to give students a framework that helps them connect mathematical ideas from one year to the next, so mathematics becomes easier to organize, easier to remember, and ultimately easier to understand. 3 straightforward questions are at the core of the Let's Count on Math framework. Here they are. 1. What are we counting? People? Meters? Tenths? Halves? Dollars? 2. How are we counting? By ones? In chunks? By multiplication? Using a formula? 3. What is this analogous or similar to? In other words, is there a simpler problem that can be used to understand the more complex one? Find the counting, find the meaning. Thank you for listening.